In this module, we will discuss the Pickett plot and the Hingle plot. Although this should be part of the discussion on water saturation calculations, I kept it separate because it requires detailed analysis that deserves attention on its own right. First of all, why do we use Pickett plots? The best method to calculate formation water resistivity is to retrieve it from the formation itself and measure its resistivity at room temperature. The log interpreter would then use that data to calculate the formation water resistivity at the reservoir temperature using the OPS equation. Now suppose no information on the formation water resistivity was provided in the dataset. How would you calculate it? Because you need it for water saturation calculation using the Archie equation. One of the options would be to make a Pickett plot, which is a graphical solution to Archie equation. The Pickett plot also helps us estimate the parameters used in Archie equation. Since we already calculated the effective porosity, we will use that for the Pickett plot. In some cases, total porosity can also be used. Let us see how to build and interpret the plot in IP.
Click on the cross plot at the top. That's one way to do it. Okay. Another way to do it is view and cross plot. So here we will select standalone Pickett plot. Pickett plot uses logarithmic scales for the resistivity on the x-axis and the logarithmic scale for the effective porosity on the y-axis. Okay, so we will choose log scale, and on the x-axis I said it is the effective porosity, so we will find that, and then on y-axis is the resistivity, true resistivity. So where is the okay, and using gamma ray on the z-axis can help you to find the sands. Excuse me. So we will also plot the gamma ray on the z-axis. And we don't need any log scale here. In an ideal case, to make a high quality Pickett plot, part of the reservoir rock should have variable porosity range and should be completely water saturated, or something close to that if we are not able to find 100% sand with 100% water saturation. However, we do not have much choice with the rock type because the reservoir is there already. Okay, so let us do one thing. Let us plot. Let us bring the log panel. Okay, so one thing we can do here is let's try to plot the sands only. Okay, so the sand goes from there up to there. These are the clean sands, and then there is slight shale in this Sleipner formation, shale and siltstone, but we should include that too. Okay, so we can type for the depth that we want to plot. It would be around 3245 to 3450 maybe. Okay, so 45 to 3450. Okay, So the gamma ray scale is from 0 to 150. The resistivity is from 0.2 to 2000, and the effective porosity is from 0 to 0.5. Let's plot it and see how it looks like, and if we need any further changes. So apply. Okay, one thing is the log scale. Since both are log scale, so we need something greater than 0. So effective porosity could be maybe 0.0, maybe 0.01, or maybe 0.0. Let's say 0.001 to 1. Okay, and then this is correct. So apply. So here you see the Picket plot. So I think let's check. I think we plotted it the wrong way. So let's plot it this way. Effective porosity on the y-axis and true resistivity on the x-axis, and this would be 0.2 to 2000 and 0.001. Okay, applied. Okay, now it looks better. Okay. Before you start interpretation, just check those things are correct or not. Here you see, okay, maybe we can use a different type of symbol. And here so these are the lines, saturation lines, 0.2, 0.3, 0.5, and this is the 100% saturation line. So let's add a 10% saturation line and a 5%. So 10% saturation line and a 0.05 for better visualization. Okay, and let's keep the same values for A, M, and RW. Okay. So look at these lines. Okay. So what we have to do is that compare this plot and see where those points plot on the log plot. Okay. So let's close this for a moment and keep it there. So what we need to do is to begin with is look for the lowest gamma ray on these plots, okay, because those are the cleanest sands. So these are the lowest gamma ray sands, okay. But what is the problem? We need some low gamma ray sands with water saturation. But what do you see here? They are saturated with mostly gas. Okay. So we cannot use this ideal situation for a very high porosity permeability sand with water content. So we do the next best thing, look for something close to that. And if we come down here, okay, we can see some points which have overlay in NP Roby. Okay, so these are relatively clean sands, if not as clean as these ones, and we can see low gamma rays here, low gamma ray values here. If you move your cursor here, just focus on this place, okay, on the right, and move your cursor here, you can see those pink points. Okay, those are the points here. So these are the points which are wet, which are 100% water saturated, and so we need to catch the trend of those points. So what we will do is we will bring our line here, the 100% line, and try to catch the trend. Okay. Highlight points. You can see that those points are these relatively clean sands with water saturation. Okay. Okay. And next If you look at the gas zone here, these are the gas zones. Okay. So let's use a different color. Let's say this one. And if we highlight these points, so what do you see? You see that the points with very high effective porosity and high resistivity are the gas zones here. Okay, we keep highlighting. Look at their gamma ray. They have very small gamma ray, low gamma ray. Sorry, that's between 0 and 15. Okay, so these are really low gamma ray sands with high porosity and high resistivity. Okay? And then if we keep moving to the left, like these points, the gamma ray between 15 and 30, then you can see these places are now being highlighted. Okay, so these are the relatively clean sands. And how about I move the cursor here? If I move the cursor at this point here, just notice the movement there. Okay, so you will see that the points along that 100% saturation line, that's where the dot is moving. Okay, so we want to actually catch the trend in this zone. Okay, so that is why we chose to put that line there, because we need relatively clean sands with water saturation to put our 100% water saturation line. Let's not highlight the points anymore, clear all and see the trends. Okay, so if you move the line here, see the RW value. See, if you pull the line upwards, then the RW value increases right here. So RW value depends on this intercept, correct? If you change the slope of this point, slope of this line, then look, both the RW values and M value, look at this point. Okay, RW and M value points are both changing. M depends on the slope of the line. See, M depends on the slope of the line, while RW depends both on the slope and position of the line. Okay, so M is what? The cementation exponent, correct? N is the saturation exponent, and A is the tortuosity factor. Now, if I increase this number N to, let's say, 2.4, you will see the separation between these lines increase. You see the separation increased a lot. And if I change this A value to, let's say, 0.5, just for the sake of doing it, and we apply, see, all of the lines are coming down. Okay, so now you can play with these points and see where you get the best match. So remember, we had a resistivity of 0.2. So if we just 0.02 last time we found that. Okay, so if we put 0.02 and M as about 1.7 and N about 2.2 and A of, let's say, 0.8, and then apply it. Do you think this is a good match? Yeah, I think so. It's a good match. It's catching the trend of these pink points, which are mostly here, 30 to 45 gamma ray value. So it catches the trend pretty well. One more thing you should notice here is that the sands have very low water saturation, which is between 5 and 10%, the good sands. And if you go a little bit down, then between 10 and 20% water saturation. Okay, so if I move the points here, you see this sand has about 20% or 18% water saturation. This one has about how much? about 7% water saturation. Even in the SW Archies that we calculated before, you can see the saturation here is about 10%. Okay, so this means there is a good match between the Archie's saturation and the saturation. Yeah, because this is also Archie. One more thing, if we want to check where these shells would plot, even though we did not plot it, but if we had to check where these shells would plot, so if we move our cursor here, then you can see, just check at this point here. Okay, so if we move our cursor at this point, you can see they are above that red line, like far from that red line. Here also they are far from the red line. Okay, so only points close to that red line are these pink ones here, uh, here, as well as these ones. So that's why we try to catch that trend. So remember one thing, as we get closer to 100% water saturation, the points will plot somewhere to the left, and we'll have this trend. And as we move away from 100% water saturation, then the points will plot to the top right, and the shales will plot somewhere in between. Okay. So for a formation, water resistivity of 0.07 ohm meter at 20 degrees Celsius, like we were given in the data set, formation water resistivity should be around 0.02, as we saw before, and we see that from the RW that 0.02 is satisfying this line. Okay, and these values are somewhat off from what we used before, but they are close. And if you want to save this plot, you can do file, save format, and you can save it as cross plot, or if you want, maybe name it picket plot, so that you can again use it in the future or look it up again. Okay, so it will be saved in the same folder for the well B. So this is well B, correct? Okay, so yeah, it will be saved under this well.
Now let us discuss the Hingle plot. The Hingle plot, like the Pickett plot, is a graphical representation of the Archie equation. In this method, you will see saturation lines fanning out of a common origin, unlike the Pickett plot, where the saturation lines are always apart from each other. However, like the Pickett plot, the Hingle plot can also be used to estimate the Archie equation parameters and formation water resistivity. Let us see how to make the Hingle plot in IP.
Go to interpretation, porosity and water saturation, and we will just check if the logs selected are correct. So density has rho B, sonic has dt. For PE, I will use a corrected PE that I corrected myself because in the given raw LAS files, the PE log was influenced by the drilling mud, which has barite, which increases the PE value. Barite has a PE value of 267, which is beyond the common rock mineral PE values of less than 6. So even a small presence of barite increases the actual PE value, so I corrected that value. Even though the PE value is not going to directly influence the Hingle plot, but whenever we enter these numbers here in a table, we should enter the numbers as correctly as possible. And for VSH, let's choose VSH mix. Temperature log we already created before, and let's choose the temperature in Celsius. For the output curves, let's save in a new set called let's say porosity, water saturation. Okay, because there will be so many outputs, and if those outputs go into the default or the calculated folder, then it will confuse us. And here you can adjust the scales. So we can go back and press OK and then press yes. So here we will zoom in. Don't worry about all the log panels here. We mainly need to right click on this RT and choose the effective porosity Hingle plot method. Okay. And then we will just display our plot that we made before. Not this. But let me check. We can go File, load plot format and plot 1, and just open it. Okay. Okay. So we will display these together. So now we can display all these zones here. Okay. So if you do not select the z-axis, then these colors will be according to the zones. For example, zone 6, 5, 4, 3, 2, and 1. But if you go to in edit format and select gamma ray for the z-axis, then this plot will be colored according to the gamma ray, and this helps us a lot because we can see which rocks are low gamma ray, and so they are mostly sandy, to which are high gamma rays, which are mostly shaly. Okay. So it's always good to make that z plot if you need it. Okay, so let's highlight, like before, we highlight some of the points, and we let's highlight the sands in red. So let's highlight the points, and you see it's highlighting the sands here. And if you if you move your cursor here, you see these are the points. So we highlight those points, and these are the sands, correct? And let's you see the sands are if you extend this 20% saturation line, sands mostly fall below that 20% saturation line. Let's also add some 10% 10% lines and the 5% line. Okay, so let's clear. Here we can plot the 10% lines. And the 5% line. Okay, and let's press apply. So we have those two lines added right there. So last time we used the Sleipner formation in the picket plot. So You can see the clean sands, relatively clean ones in the Sleipner plot somewhere in this zone. And if we want to choose just the points in Sleipner for our fitting purpose, then we can right click here and highlight cross plot, and then we can highlight this entire zone. You see, by highlighting that entire zone, we only have those points displayed which are highlighted here. Okay, so this makes it easy for us to fit our line. This 100% saturation line, we can fit something like this. Okay, okay, uh, okay. So we can then remove this highlight and display all the points here by clicking on the clear cross plot highlights. Now all the points are displayed there. Okay, let's see how the lines, these saturation lines, behave if you enter different values for these Archie's parameters. If I increase RW value to 1, just see how those points will move. Not the points, but actually the lines. Okay, you see, we have an impression that our line moved to the left relative to those points by increasing the RW value. There was a slight shift, but we saw that, right? So let's change RW back to 0.02. See, okay. Then we can see the effect of M. So let's change M from 2 to now 3. What did you see here? These lines effectively shift to the right, correct, with respect to the points, because if you extend it there, then these lines are to the right. See, it would go somewhere there. Okay. Then we can change it back to some reasonable value of 2. And how about the value of n? If we change n from 2.2 to 4, apply, what happened? You see that the distance between this 100% saturation line and this 50% saturation line increased. Okay. Similarly, there was some adjustment in the distances between these lines, just like we had in the Picket plot. So we can move it back to some reasonable value. And how about if we change A? Let's change it to 1. You see again, there was a relative shift in these lines towards the right, okay, by increasing A value to 1. So let's change it back and see. 0.08, sorry, 0.8. See, they moved to the left, and then when we change it to 1, they move to the right, those lines, right? So let's check if those values are reasonable. 0.02, let's put A equal to 0.8, which is there, and then M, let's put 2.1, and N 2.2. Apply. So I think these lines catch the trends pretty well. Okay. So yeah, it's catching the trend pretty well. Okay, and we can see that the 0.05 line, if you extend here, then these points will have about 7 to 10% saturation, which is correct. So now if you are satisfied with these values, you can use these in your Archie's equation. One more thing you can do with these cross plots is make user lines. Okay, so function create user line, click there, and then make some user line. Okay. So now you see there is an equation of that user line, which is y with respect to x. You can make another user line by clicking here. So this is how you will create user line if you wanted to see the trends. And you can even delete the user lines. So just choose this one and delete it, and then okay, so delete it. Yes, you choose next one and delete it. Yes, so now it cleared the user line. This was just for your knowledge. One more thing is we can now close this one. Remember these values, it's close to 0.02, 2.1, 2.2 and 8. Okay, so okay, and then we can close this. So now one thing you could have done here also is instead of PHIE, which is the effective porosity, you could have also used the total porosity. Sometimes there's a bit of glitch. So it should display those lines. See, now they are displayed. You might have to play with a little bit to see those lines. So now you can also play with the total porosity instead of the effective porosity. Uh, so you can go choose multiple zones, and then you can see if with those numbers you like it or not. So if you want to shift it a little bit downwards and see how it changes those values, if you just use 0.02, yeah, so you will get slightly different values then depending on how you adjust these lines for this R, W, M, N and A. So it would give you slightly different values than using PHIE instead of PHIT, but ultimately it depends on the interpreter, and the interpreter needs to justify the values obtained from these methods. So again, you can play with the same things, these highlighting points, correct? So you can highlight again here and see where those points plot, or you can clear all and then just choose these points. Okay, so it looks pretty good to me. So yeah, this is how you will do your interpretation. I'm showing you in very short, but actually this whole thing could take you maybe 3 or 4 hours to do it correctly, because if you want to do it for a company, or if you are doing it for your thesis, then you will need to spend a lot more time than this demonstration.